Hello there, you're in the lab with your mate JJ. Today is Learning the Art of Electronics Day. While I think of it, today's silly job title is Systems Architect. Today I'm the Systems Architect. That doesn't sound so silly after all. I bet you there's people called Systems Architects out there. Anyway, today the system we'll be architecting will be another circuit from Learning the Art of Electronics, which is our coursework. This is the book. We'll be going over to the bench, having a look in the book, finding what circuit we're going to do. We'll do the experiment, and then after that we'll come back and we'll review our notes. The notes include some revision from the stuff that we covered last week. And the new format of the Learning the Art of Electronics videos is that we do the experiment first, because that will be the new material, and then at the end of the video, in the back half of the video, we'll do the revision and look at the stuff that we've seen a lot of before. Of course, the purpose of this material is to learn about electronics, and spaced repetition is a good way to learn. So doing revision of the material I think is just beneficial, so I'm happy to do that. Take a bit of time to do that, but first we'll pop over to the bench and we'll do the circuits. It's last week we investigated analog multimeters. This week we'll be investigating digital multimeters, and of course they do behave a bit differently, because the analog meter uses essentially a current sensor, whereas the digital multimeter uses a voltage sensor, and consequently it doesn't disturb the circuit as much as an analog circuit does. So yeah, let's jump over to the bench together and we'll have a look in the book, and then we'll make our circuit and do our investigations. Then we'll run over to do our notes, and then we'll wrap up. Here on the bench, and this is our book. Can you see that? I hope you can. So let's jump ahead to where we're up to. Looks like we're going to be on page 20 here. So last week we started investigating this circuit, and we did it with this range of values, and this range of resistances, and then we had a look at this. So this is all material that we've covered. So as we said earlier, an analog meter senses current in its guts, and a digital meter senses voltage in its guts. So there's a specification on the analog meter that says how many ohms per volt it introduces into the system. So it describes the sensitivity of the meter movement, which is the guts of the instrument. This movement puts a fairly low ceiling on the voltmeter's input resistance at a given range setting. And then it says here, let's try the same experiment with a digital voltmeter, and let's suppose we get the following readings. So we're actually going to take these readings, and that's what we'll be doing today. And as you can see, the expected outcome is at 10K and 1 meg. We're pretty close to the 10 volt theoretical, but if we go all the way up to 10 megs, the loading becomes obvious. It says here again, let's use the case where the droop is obvious. Again, let's talk our way to an answer. This time the Thevenin resistance is 5 meg. We're dropping 2/3 of the voltage across Rin-DVM, 1/3 across the Thevenin resistance. So the resistance in the input resistance of the DVM must be 2 times the Thevenin resistance, or 10 meg. If we check the data sheet for this particular DVM, we find that its Rin is specified to be 10 meg, all ranges. Again, our readings make sense. So here's figure 1N.29. DVM reading departs from ideal. We can infer the input resistance of the DVM. Okay, cool. So we're going to set up this circuit. recently I wired in my new Tenma power supply, so I'll be able to use that to provide 20 volts. I won't have to scale everything back like I did in the previous videos because I now have the capacity to deliver 20 volts on the bench, which is really great. So just 1 second, I'll get set up. All right, I'm back and I've got the equipment we'll be using. This is our multimeter here. It's all wired up with the power supply that comes in here. We've got it on a switch here. I can show you if I turn it on. The reading is 19.99. If I turn it off, it goes off. So what we're going to do while it's switched off is we're going to run we're going to run the power into the top. So let's send, we'll just send positive in this way. And then we're going to connect this to this, which we'll do with, let's say, a blue jumper. Okay. And then we're going to power it at the bottom. Now, before we do anything, let's make sure all the resistances are off. And our first resistance, I'll need to get myself the old notebook. Can you see that? Yes, I think you can. All right, so get myself a fresh page with the notebook. I'm not sure what the date is today. It's the 16th of September. So I got a little bit behind on my Learning the Art of Electronics videos, but I think I'm going to make it in time for today. So this is 16/9/2025, and we'll be doing, let's say, Fig, LAOE, Fig-1N.29. All right. And we're going to be testing values of V out. So we're going to have R at 100K, 100K, and then 1 meg and 10 meg, 1 meg and 10 meg. And we're going to get a reading for V out. V out, that's what we will measure. That's the output of our DVM. Okay, now we're going to need to put our what am I trying to say? Well, we're going to have to plug in our multimeter. So we're going to want to test the this point and this point. I've got to put that in. Oh, that's annoying. All right. Well, how are we going to do that? I think we're going to need to run an extra lead. That's no problem. So we'll run an extra black lead. Just piggyback it off here. And that yellow terminal shouldn't hurt. It's of course not necessary. So, and we're going to need to wire in our multimeter, which is going to go across the R2, which is this bottom resistor here. So we'll put black there, which is common, and then we'll put red here, which is positive. All right, now we haven't turned it on yet, and that's good because we haven't put any resistance in yet, and if we don't, it'll short circuit. So we need to put something in there, and it needs to be 100K. 100K on the top and 100K on the bottom. So here is our 100K. All right, now we've got our resistors wired in. I suppose I might as well sketch the circuit for you as well. Let's do that quickly in time lapse. All right, so this is the schematic that we're putting together. We're sending 20 volts into our supply. R1 will be set at 100K, 1 meg and 10 meg. And each time it is, we're going to be measuring the voltage between this point and this point. We'll be able to use those voltage readings to figure out what the internal resistance of the digital voltmeter is. So we've got our resistances set to 100K. Hopefully we haven't made any mistakes. So when we throw the power switch on, great. So we're reading V out as 9.93, which is pretty close to the 10 meg that we'd expect. So we'll turn the circuit off, and we're going to change our things to 1 meg. So I've readjusted the circuit. We're now measuring 1 meg. Let's turn him on, and the reading is 9.52. 9.52, dropping off a bit, but still pretty close to 10 volts. And now we're going to do 10 meg. So 1 plus 2 is 3, plus 3 is 6, plus 4 is 10. Okay, with all of those on, that's 10 meg. 1 plus 2 plus 3 plus 4, 10. Very good. So let's get a reading for that. We'll throw the switch, and we're looking at, well, it's jumping around a bit. There we go. It's settled at 6.69. 6.69. Great. Now, let's use these numbers to figure out what Rin here is. Rin's what we're interested in. Let me just take a break, get more coffee. I'll come back and we'll keep on keeping on. First, I'll turn this off. I'll be back in a sec. Okay, I'm back, and I've got my coffee, which is very important. So let's add some columns to our table. Let's add R Thev. Now, in all cases, R Thev is going to be half of whatever this is. So that'll be 50K, 500K, and 5 meg. And what we want is R in. So let's put R in over here. That's what we want to calculate. Now, the way to do it is to say that if V out is across the Thevenin, and it's 10.69, that means that 10 minus 6.69 is the voltage across the Thevenin circuit. So we might actually even just calculate or we could just say that the Rin, how to get that? We need to know the Thevenin. The Thevenin voltage is is 10 volts, and the actual voltage is I'm running out of space. So let's say we want 10 minus V out. And that 10, by the way, is the R Thev. So this is R Thev minus V out, which is 10 minus 6.69. It's about 3.3. Might as well get it exact, although that's a bit silly. Anyway, so we've got 10 minus 6.69, 3.31, 3.31. So I don't know how to say it, but what we want is 3.31 is to 5 meg, as 6.69 is to the Rin. So that means that that Rin is 5 times 6.69 divided by that, which is so 6.69 divided by 3.31 equals that times the Thev, which is 5 meg, and the answer is 10.1. 10.1. We'll call that Rin is 10.1 meg, which is which stacks, doesn't it? So let's do the same for the other measurement and see how that comes out. So that'll be 10 minus V out is what's it, 0.48, isn't it? Might as well do it just to make sure I don't make any silly gaffes. So we're going to go 10 minus 9.52, and that's 0.48. And then we'll do the same thing down here, is 0.48 is to 500K, as 9.52 is to Rin, which means that we'll just do 9.52 9.52 divided by 0.48 equals times 0.5. 500K is 0.5 of a meg, and the answer is 9.91. 9.991. 9.91. And we've kind of run out of space down the bottom here to do the next calculation, but it'll be the same. You just figure out what proportion of the voltage is being dropped across the Thevenin resistance, and then you can calculate how, and you know how you measure how much voltage is being dropped across the output terminal and ground, and then you just set up the ratio and solve for Rin, which is basically this divided by this times this equals this. So I think that concludes the experiment for today. So the next thing to do, of course, is to jump over to the computer and go through our notes, and that will include some revision from what we covered last week, and it'll include the notes from today's reading as well. So let's jump over to the computer together and have a look at the notes. Here on the computer. So Today we're just going to review our notes for chapter 1N, which we're working through. The notes have been fleshed out a little bit since last week, and I've integrated the experimental results from the experiment we just did. So let's see if we can find our notes. This is subscriber only material. You can get access to it if you support me on Patreon. So, but you don't need to do that. We can just go through it together ourselves now. So I'm just going to jump ahead to the chapter 1N DC circuits, and I'm going to run you through the notes. We've seen this before. We've seen this last week, but there's some new material at the end. So this is the first chapter in the book. We're going to learn how to make a voltage divider. The subject of this course is the laws, rules of thumb, and tricks that constitute the art of electronics. When delivering power to something, that something is called a load. This course is concerned with using electronics to model and process information. We're not super interested in power electronics, which has to do with delivering power to things. We're interested in modeling and processing information. They asked the question, is it better to model information with voltage or current? And the answer is that a voltage is better because current uses power, but voltage doesn't necessarily use power, and certainly not very much. We need to be familiar with Ohm's law, which is V equals IR, where V is for voltage in volts, I is for current in amperes or amps, and R is for resistance in ohms. As they say, a volt is what pushes an amp through an ohm. There you go. 1 volt is the work done as one adds 1 joule of potential energy to 1 coulomb of charge. It's another way of formulating, or it's another implication of the law. Ohm's law is useful, but it only applies to resistors. And a lot of things aren't resistors, as we'll learn soon. The inverse of resistance is conductance. Electrical conductance is given as G, and G is the reciprocal of the resistance, so that's G equals 1 on R. Conductivity degrades, increasing resistance when temperature increases. So usually if you heat something up, it doesn't conduct as well as it did, so its resistance increases. It's not true of every material, but it's usually true. We've got a mathematical expression here that the energy of the electric field is given by voltage over distance. There you go. That's 2 points. It's points. Okay. I don't totally get this yet. The physics is still a bit beyond me. There are various strategies for making a resistor. We've got carbon composition, carbon film, metal film, and wire wound. Many electronic components do not obey Ohm's law, as we mentioned already. So don't expect to use Ohm's law where it doesn't fit. It only works for resistors. But we can extend the reach of Ohm's law with dynamic resistance, and that's given as the dynamic resistance is dV di. So the change in voltage divided by the change in current. And then we can talk about the effective resistance of various devices such as diodes, transistors, current sources, or whatnot. And that's given in this diagram here. You see that the standard linear resistor is just a straight line. The lamp does this kind of thing. It changes as the filament in the globe gets hot. The diode does this weird little thing like this. And a current source is just straight up line at off to infinity at the point. That's an ideal current source. You will never find an ideal current source in an experiment. They've switched the axes here. So usually it's I versus V, but it's given here as V versus I, so the tangent, the units come out in ohms. And in this case of our diode, at 150 ohms with 0.2 milliamps, the dynamic resistance is given.
Oh, yeah. So the tangent of the tangent is the dynamic resistance. Okay, so power is the rate of doing work. Components will have power ratings. So if your component has to dissipate a certain amount of power, make sure that it can. Usually that comes out as heat. Sometimes it comes out as mechanical work or light. Formula for power in watts: P equals IV, P equals I squared R, and P equals V squared on R, which is of course just courtesy of Ohm's law. To find the minimum resistance for a quarter watt resistor at 15 volts, you put in 1/4 watt equals 15 squared on R min, and then you solve for R min, you get 225 divided by a quarter equals 900 ohms. So 1 kilo ohm is close to the minimum safe value at 15 volts. And of course, the value does change depending on the voltage. So, yeah. Current measures charge over time, and voltage measures work per charge. So if you put those together, the charge cancels and you get power is work on time. In this course, we rarely worry about power, so we don't care a lot about power. But we do care a little bit about power some of the time. So now we need KVL and KCL. KVL is Kirchhoff's voltage law, and KCL is Kirchhoff's current law. KVL says that the sum of the voltages around a loop is 0, and Kirchhoff's current law says that the sum of currents in and the sum of currents out are 0. And that, of course, is the algebraic sum, so the negative currents cancel. So we've got the series current. The total current is the same at both currents. Parallel current, they add. Series voltage, the total is they add, and the parallel, they're the same. And here's the diagram that goes with those claims. So the current through here and here is the same. The voltage from here to here is additive, whereas this way the current through here and the current through here add, and the voltage from here and the voltage from here are the same. I have to say, getting my head around the details, I'm a bit of a sloppy thinker, I think. Anyway, that's what we've got. Here, of course, you need to be aware that that the circuit actually exists. This bit here and this bit here actually tie off like this, so it is a circuit. This might not look like a circuit because it's not circular, but it is, because this point doubles back to here, and that's why we call it a circuit. So you should be familiar with that. This is just a classic parallel resistors setup. Now, when it comes to parallel resistances, it's the conductances that add, which means it's the reciprocals of the resistances that add. So if you solve that for just 2 resistors in parallel, then you can get an expression for the total resistance, and it's R1 times R2 divided by R1 plus R2. And then here's some R's for some typical cases. If they're the same, then the result is half R. If one's small and one's 10 times bigger, then it's actually just that ratio of the small one. So this is 10/11ths of R. And then this one, R and 2R, you've got them in proportion, so that the resistance of the whole circuit with these 2 parallels is just 2/3 of R. This is good to know. In a parallel circuit, a resistor much smaller than the other dominates. So the small resistor in parallel will win out, and in series, the large resistor wins out. This has the most effect. Oh yes, since last week I added this note. When using a potentiometer as a variable resistor, it's a good idea to tie one end to the wiper. This means that if the wiper comes loose, the maximum resistance is seen instead of an open circuit. This can be important as you probably haven't tested your circuit with an open circuit resistance from this component. So the idea is if the wiper gets old and comes loose, the circuit will still run through the maximum resistance of the potentiometer as the variable resistance. So instead of going open, it'll just go to maximum resistance, which is probably better for your circuit. So better fail safe. So get in the habit of doing that. If you're just making a variable resistor, tie the wiper to one of the one end of the potentiometers. There's a potentiometer is a 3-terminal device, and a variable resistor is a 2-terminal device. So just tie off that third terminal. Here we go. We're looking at a voltage divider. I think we're starting to get the hang of that, aren't we? We've got the top resistance and the bottom resistance. We've been doing a lot of work where they're the same, so that the numbers come out nice. Anyway, here again, it's just this is us figuring out the current, which is the same through the whole thing, which is Vn divided by R1 plus R2. Which is 1.5 milliamps. Then we can use that to calculate V out, and we get V out as 15 volts. That's one way of calculating the result of this circuit. But there's another way. This is the second method. So we know that I is the same in top and bottom, which means that we can put the expression in terms of resistance, voltage in terms of current and resistance, and then the currents cancel, and we're left with an expression in resistance, and that allows us to compute the output voltage by multiplying the input voltage by this expression here, which is just basically leaving R1 out. So you keep the bottom half and you divide by the sum, and then you get an expression for V out. It says here, we will use the formula 1N1 fairly often. I need to do something with the notes to make this this a little bit more sort of prominent anyway. So and then the third method they give you for calculating the Thevenin voltage is just to muddle it out in your head by making a statement. Since the currents in top and bottom are equal, the voltage drops are proportional to the resistances, which later we'll be calling impedances. So in this case, where the lower resistance makes up half the resistance, it will also show half the total voltage. As another example, if R2 is 10 times R1, then it will show 10/11ths of the input voltage, roughly 91%. Loading and output impedance. Next, we need to think about what we do if someone comes along and adds a load to our circuit. So that's what we're going to be investigating there. The tedious method is to treat the bottom bit as a voltage divider, compute the Thevenin equivalent, or not. That's not even just compute the parallel voltage, and then redo your calculations with 10K at the top and equivalent 5K at the bottom, and get yourself a result. And that will certainly work. But if you want to do that every time you change this, you'll have to go through the whole thing again. There's a better way, and the better way is called Thevenin's model, which is something that we're learning about here. So in the Thevenin model, you ignore the load, and you take the you look at this point here, the V out point of the voltage divider, and then you get the parallel resistance from the top part and the bottom part. So the parallel resistance of R1 and R2 is what they call the Thevenin resistance for the model, and the open circuit, what that means when there's no load attached, then the Thevenin voltage is just what V out would have been with no load attached. So I'm not seeing a lot of green here. So yeah, the Thevenin voltage is just V out from the divider, and the Thevenin, as we said, is R1 in parallel with R2. Now they spend some time trying to justify the Thevenin shortcut, and honestly, it goes over my head every time. But basically, you just look at this point here, and then treat the stuff on the top as in parallel with the stuff on the bottom, because they tie off at this point. This was a general definition and procedure for determining impedance at a point. To discover the impedance at a point, apply a delta V and measure a delta I, and then the quotient is the impedance. So that's given here as the impedance is the change in V on the change in I, which in this case is 1 volt divided by 0.2 milliamps equals 5 kilo ohms, which is what we wanted. So it turns out that this value, Rthev, is what we come to know as the output impedance. They're the same thing. And there's a section here where I asked ChatGPT about are output impedance and Thevenin resistance the same thing? And it said in practice they're the same concept. And then it goes on to take you through some explanation there, and it comes with this conclusion: output impedance and Thevenin impedance are the same. If you're only dealing with DC resistive cases, Thevenin resistance is the same as the output impedance. Then we're up to applying the Thevenin model. So we do that here. We take the load and we model this part of the circuit as a Thevenin model, and we get the same values as we'd expect. And yeah, they call it the droop. The droop. I asked ChatGPT the question: if output impedance measures how stiff or droopy an output is a higher output impedance more droopy or more stiff? And it's more droopy. So you really want a low output impedance, and then you'll get the most power of that, most voltage available on the output of your voltage divider. Okay, so suppose that we try to measure V out at the output of each divider. If we measured with a perfect voltmeter, the answer in all cases would be 10 volts. Okay, and it says here, is it 10.000 volts or 10.0 volts? And the answer is it could be 10.0 volts, but it could equally be 9.9 volts or 10.1 volts. So that we can't expect perfection. If we perform the measurement, we see the effect of loading by the Rin of our imperfect lab voltmeter. So over here, we're doing the there's two different voltmeters that we test, the analog one and the digital one. But in both cases, the internal resistance of the voltmeter is going to affect the results. If this were perfect, we'd get a perfect 10 volts, but we won't because of the input impedance, or the resistance of the internal resistance of the voltmeter. And this is what we did last week, which was measuring these values. We tested this experimentally. Of course, they gave us these numbers in the book, but we calculated our own numbers. I didn't make a note of that in the here. I missed that. So, of course, things have changed a bit now where we do the experiment before we do the notes. So this week I can actually include the results of the experiment in the notes because I've done it already. So this again is talking ourselves into a solution for the resistance, the input resistance of the voltmeter. So as we see here, this 8, the meter shows us 8 parts in 10 across the dividers. R Thevenin or R out, same thing, must be dropping the other 2 parts in 10. So you lose 2 here. The relative sizes of the 2 resistances are in proportion to these voltage drops, 8 to 2, which is 4 to 1, which means that the internal resistance of the VOM is 4 times the Thevenin resistance, which is 200 kiloohms. And then again, for the VOM, the analog meter, we did indeed find that it was 20,000 ohms per volt as the spec on the multimeter, and we got 200K because we were on the 10 volt scale, so that's 10 times this, which is correct. So there we go. But that's what we did last week, and as we learned, the analog meter senses current in its guts, and the digital meter senses voltage in its guts. And that actually is part of the reason why this has a better output impedance, as we're about to discover. The note here is that the VOM specification of 20 kiloohms per volt describes the sensitivity of the meter movement, the guts of the instrument, literally in here in the electromagnet. Yeah. And then there's some notes. Please explain a meter movement to me. So I got ChatGPT to talk me through what that meter movement is. It's a noun, and it has parts and operation and so on, and it runs us through some calculations. I didn't have a close look at these, so they could be right, they could be wrong, who knows. I didn't have a really close look. I might have a close look at some point. It's certainly there for me to do so. So let's try the experiment we did with the voltmeter, and here's the experiment that we did today. So let's try the experiment we did with the analog meter with our digital meter. And these are the values that that were given in the textbook, and then they talked us through to an answer here, saying that the RThev is 5 meg. We're talking about for the bottom case here, and we're dropping 6.69 volts out of 10. This is the circuit diagram. We've got 20 volts in, means that V out is 10 volts, and there's a 5 meg Thevenin resistance. This number here we measured. We measured this point and ground. That's what's being dropped by the internal resistance of the DVM. And then that's approximately 2/3, which is approximately yeah, anyway, so the result is 2 times the Thevenin resistance, which is 10 meg, which turns out to be what we want to see. And that's what we did today. So we ran the experiment for we ran the experiment feeding in the 100K, 1 meg, and 10 meg resistors. Here's drawn for the 10 meg. And then we measured V out, and we got these values, which were they very similar? 9.92 and 9.93, that's pretty close. 9.55 and 9.52, that's still pretty close. And 6.69 and 6.69 is exactly the same. Isn't that funny? as I say here in the above table, R was given, V out was measured. This was what we measured. Everything else was calculated. So we calculated this, we calculated this, we calculated this, and we calculated this. And this Rin-DVM, this is the internal resistance of our voltmeter. 10.1 meg, that's a very good reading. 9.91 megs, also pretty good. 7.09 megs is a bit out of the money. So probably some rounding error there, precision stuff. But these two measurements are right on the money. And as we say here, the multimeter that was used was the EV blog BM2257 multimeter, and there's a link here to the blog, to the meter, and it says page 19 of the user manual lists the impedance while in DC voltage mode as 10 mega ohm, which agrees with our calculations. And I put here just a note, I'm not 100% sure why we only got 7.09 meg for the first experiment, but I expect it has to do with resolution of values taken. So, is that everything? I think it is. So that concludes the notes for this week. We'll be looking at them all again next week, of course, as we continue on to the next experiment. So, yeah, I think that brings us to a close. So I'll throw you over to the farewell cam and we'll wrap up.
And that's a wrap. So what did we learn today? We learned that the digital multimeter has a much higher internal resistance than the analog voltmeter. The consequence is that the meter affects the readings less. So the analog meter had an internal resistance of 20 kilo ohms per volt, whereas the digital meter had 10 mega ohms for all ranges. So it can measure the output voltage to a higher number with a greater degree of precision. So yes, I think that concludes this video. So I hope you enjoyed this video. Thanks very much for watching, and please remember to click like and subscribe.